Thomas Vertinger, sitting amongst you. He's not a new student who's just joined the course. He's actually the lead implementer and inventor of a lot of the truffle stuff you saw last week. And so what we can do this week is, well, firstly we have a constraint that at 4:45 we have the survey person come in who will ask you things and just say yes to all the questions. Yes and 10 or whatever the scoring system is. Between now and then I have some material on implementing objects and methods in Truffle, which we'll look at. I have the beginnings of the stuff on concurrency in VMs. Thomas has some stuff on Truffle and the project Oracle and kind of what we're doing with it and all the various directions. And we can also do kind of a clinic on your Truffle code if you need that. So sort of try and get the sense of the room. How's it been going this last week and a half with your Truffle implementation? How many people have got a working program? Excellent. Because I kind of threw you in at the deep end last time, to be honest. You kind of got them maybe just enough to actually make progress. Maybe not even that. Anyone want help? Got questions? Stuck? No?
Maybe you could explain the materialized frame some more.
Explain
the
it.
materialized temporal frame.
Yeah, sure. And I've got just to kind of be sure that this was doable. I did it myself. Took a couple of days to get a working implementation. So I have that we can look at. It's not very fast. It's not optimized in any way, but it works, or at least it works on the programs I've written on. So we can use that as a. So the materialized frame stuff. Let's look at that. See if I can. I'm probably going to have to mirror this because I can't really look at that screen. And if I spin this around, I can do it. Well, so there you go. It runs. Does work. Not super fast, but there's no caching of any kind. If we look at the layout is all So the way I did the scope stuff is I have a materialized frame which represents the top level environment. I make that a compilation final because if there's only one of them, it's never going to change. And then I have a stack of frame descriptors that represent nested frames. I think really for FINA, I probably only need one, maybe two methods, and then the function that the method is in. Probably need two, right?
It depends on how you handle like the if statements and while statements.
Okay.
Because they have their own.
But
scope.
the stack is a nice general solution. So I just use a Java util thingy to build a stack of frame descriptors, and then when I compile a variable, show you that. Here. So every node I have a truffleize method which generates the truffle AST. And all I do here is I look up on the top level frame descriptor if it's there. I should really go down the stack, but I cheat it. So this looks it in the top level. If it's not declared in the innermost level, if it's not there, it goes to the top level, which I think works fine for function because you can't nest functions, right? Yeah. And then generates one of two node kinds depending on where it finds the frame slot. So the frame slot is then stored in the node, and when I execute a local, so here I have specializations for int and object. There I take the frame that was passed in and I do the lookup in that frame. If I'm reading in a global, I just go straight to the top level frame and do the lookup there, and I ignore the frame that was passed in. And that works fine. It's very direct. What else is there to say about this? Well, we'll maybe look some more after I've talked about the objects and methods stuff. Okay, so the parts that are missing in your implementations, you don't have objects and you don't have methods unless you've sort of figured it out for yourself. And then all the performance enhancements that make those things fast. So I wanted to talk a little bit about the object model and how you implement objects. So Truffle, that's one of the most recent additions to Truffle. It supports objects, dynamic objects with varying shapes, because that's the common way things are done in scripting languages like Ruby and JavaScript. You get some you can add and remove slots on the fly, and that's actually done in real programs, unlike class-based languages or in Self, where those are programming operations and not expected to be happening at runtime. So you get this abstract class called dynamic object, and dynamic objects is implemented in such a way that it can track the shape of the actual runtime object, and by shape I mean the number and names of the properties and their types. And if the shapes change, as they do in most systems, relatively infrequently, so you're not every line changing them, and you're changing them in a few ways, each path through the program has its own set of assignments, then it'll record the shapes and it can transition between them and cache them to get fast read and writes, as if you'd implemented them sort of in a class-based language. So let me show you some pictures to explain that. Underlying each object, there's a thing called a storage object. And a storage object looks a bit like a regular object, except it has the shape reference. Now, in the object header, because it's a Java object, there's a Java class that it points to. But the way to think of this is the shape reference is a bit like the map in Self. It points to something that is the metadata for how stuff is laid out in here and how to look things up. And then, because this is implemented in Java, and you have to statically distinguish between primitives and objects, these things are divided up into sort of a little resource, memory resource where you can put primitives, and another one where you can put object references. So the GC knows to only look in here for references to objects. It won't look at this at all. You can put floats and longs and other stuff in there. And then the shape tells you everything you need to know. So what if you need to make one that gets really big as you add properties, because that can happen at runtime. You can be adding variables ad infinitum. Well, these things are fixed in size because they're Java objects, but you can use the object storage area to contain references to extension arrays, and the extension arrays can hold more primitives and more object references. So there's a little bit of a space and performance cost in this relative to a direct implementation as you would do it, in a VM custom for your language. But this is sort of the best you can do in Java in a generic way, because as I said last week, last time, you've got a statically typed language at the bottom, and you're implementing dynamically typed stuff on top of it, and there are going to be places where those things rub against each other badly. And this is one example where you have some space and speed penalty in the event that you make a really big object. Now, there's enough space in these typically that for most objects you shouldn't need the extensions. So how do you deal with the shapes and the shape transitions? Well, as you add or remove properties from an object, a new shape gets generated or looked up if it already exists, and then the object transitions from one shape to another. So assume we're in JavaScript, we make an object that's empty. What that's going to look like in the underlying implementation is a header and a reference to an empty shape. And the storage area isn't going to contain anything. Then as we write to a slot, the new shape will be computed that says, okay, this shape describes an object that has an X field that's an int, so it's stored in the primitive area, and it's the 0th index into that area. So in this case, where the 4 is put, and that's where Now, obviously, when you want to look up an X, you have all the information you need in the shape to find which slot in the underlying storage you could find it. If you now add another slot, a new shape is generated. That contains the extra description, and the object is modified in the appropriate way. Now, suppose we change the X field to be a string and not a primitive, and what's going to happen is we generate a new shape which contains X as being stored as a string in the reference area, and the reference to the string will be stored there as sorry. Okay. That clear? Fairly straightforward. The shapes themselves are immutable. They sort of never change, the shapes themselves. You change only the underlying objects, and they're canonicalized. So once you want to look up a shape, if there's an existing shape that describes the structure you want, you find that. So there's no duplication of them. And so that means that the identity of them can serve for equality. If you want to compare two shapes for being the same, if they're different identities, they have to be different. And then a transition map is used to connect them together so that when you have a shape and you have a request for a property addition or a type change or a property deletion, you can find the next one if that transition has already taken place really quickly. There's not much computation involved. First time you have to do some computation and maybe creation of a shape, but otherwise no. So this is the kind of the full picture. You have the storage object over on the left, which references the shape, and then the shape references through its transitions all the other new shapes that it already knows how to get to, and then off in here there are properties. So let's look at each. So each shape has a predecessor, which is how you got here. They form a tree, and then here's the references to the transitions, which take you to all the successors, the descendants in the tree. And then for each of the fields, which are called properties in this model, you have a property object, and the property object gives you the key, which is whatever you use to look the thing up, the name of the thing, a location, which is the place in here that it's stored, and you can have some attributes associated with it too. For things like, some properties can be hidden, they can be implementation only that the application doesn't get to see. Like in JavaScript, you've got prototype fields and stuff like that. There's a bunch of variations there. And then the allocator is a separate object here, which is used to track the space used in the underlying storage and reshape that as it's needed, generate the extensions if those have to be generated, reclaim them if they're not needed anymore. And all of these can be implemented or re-implemented by subclassing. But this is the generic base model. And then one of the attributes that's allowed in a property is a shared attribute, and in that case, the property is stored directly in the shape and not in the underlying object. So if you have an immutable user-level thing which can be shared across all the instances, that can go in the shape rather than a copy of it being painted in each object. So then the shape transitions themselves form a tree. The root is always the empty shape. And as you insert or remove fields, you traverse down this tree. And the tables that are attached to each shape are used to look up the next shape if you've already seen one. So here's an example of what the tree would look like having executed a piece of JavaScript. So the first 3 lines that we had earlier, and then a couple more lines that make a couple of other objects with other shapes. So we have one here with X and Y that are strings, and another one with X that's a string and Y that's an int. Then you end up with a shape tree like this, so that when you make an object, it would be this shape, and then when you get an assignment to a new property, If it's one that you've already seen, you just traverse your way down the tree, computing the new shape, and that gives you your storing things. So if you want to actually try and program this up for yourself, it's fairly straightforward. You have a thing called object type that your underlying object type should inherit from. Actually, in the implementation I did, I just used object type directly. You make a layout object, and that can be used to create empty shapes. So here's how you make an empty one. And then to make an instance of an empty shape, you just say new instance to the layout. And then here's the code for doing the updates. To add a property with name n and value v, you grab the shape, the shape as it currently is, you compute the shape as it would be after you've added the slot with n and v as values. From that you can then get the location of where you're going to write the new value in, and then you can set the value of the slot having got its location. If it's already existing, then there's a quicker way of doing that. And then to read a field, you get the shape, you get the property, you look up the location in the object. And the shapes can be cached. So one enhancement for the Feeney implementation would be to compute a shape for an object and then cache it with an object node, so that when you make an object, you already have the, because the shapes are constants. Okay. So once you've got this, then to make it fast, you want to do inline caching. And Truffle provides a way of automatically building inline caches for you to speed up dispatch, and it automatically will generalize your inline cache to a polymorphic inline cache if needed. In the interpreter, you do stuff via type tests and specializations, and for object properties, you use shape guards. So if you write a simple class with specializations in, then the system, when it dispatches the operation here that's being implemented, it will automatically add in the dispatching appropriate to make inline caching. So for example, for property accesses, when you write the code, it will initially use an uninitialized cache, and as you add more types in, these guards will get added, and associated direct gets of the properties. And if you go megamorphic, then it'll fall back to an indirect lookup. And the Truffle DSL implementation involves writing specializations where you put in a cache that says, okay, I'm only executing this case when my operand matches our cached operand. You can give a limit to how many different variants it will hold, and then you do the generic version, which it falls back on if the guard
What do you mean by
isn't matched.
megamorphism?
I'm sorry?
What do you mean by megamorphism? Is that
So when you've got too many types.
Okay.
So in this case, if you've got more than 3 different types, it would fall back to the generic case.
Okay.
And then you can do a similar thing using type tests to do cache lookup. Okay. Any questions?
So in the implementation, when you have a guard like operand.get class,
Yes.
is that pattern like specially recognized? Or
No,
does it
these
actually
are
look
just
up?
pieces of code that get plugged in at the appropriate places. The fact that there is a guard means that the template for a guard test will be generated, and in the body of the guard test, this code will get pasted in for you to say, okay, we execute this test, and that's how we dispatch between the cached and the uncached case.
Okay. And like to implement a full .get class thing is like non-trivial, right? You look up the header word and then you look up in your table of class objects. Is Truffle smart enough to not do that?
A get class of...
An arbitrary object.
Oh, I see. So the underlying VM will be doing optimizations
Oh, I
around
see.
that,
Okay.
right? Because you're just running on top of a JVM.
Oh, okay. Yeah.
Crown will do in this case the optimization because it's a class check on Java.
Okay.
Yeah. So when it's compiled, Graal recognizes whatever construct you've used, you know, in terms of just doing Java optimization, and will apply it. You know, it's just seeing sort of this big chunk of Java code that got generated from the code you wrote with the annotations, and it just does whatever it normally does in those things. Thomas, do you want to?
Yes,
Go next.
I'm ready. I'm ready.
Good.
I'm ready for the whiskey life demo. So let's see. I just got it tested 5 minutes ago, so that means the next 5
It
minutes
must work,
it should still work, right? Oh yeah, this is it. I might need to sit. Can I sit here?
Yeah, sure. Special spider.
And I might need a.
You should wear this.
Excellent.
Members security services.
How do I?
Just over your ear.
Other.
Here?
Flip it upside down. Flip it upside down.
Yep.
Upside down. Flip it upside down. Yeah.
Excellent. Couldn't you do that?
It's first
Oh.
It's like
Wire in
wrong
front of
or
his
wrong.
face now.
Alright. Yeah, we kind of need to. PowerPoint has encountered a problem. But we don't send, but we also don't restart. We don't need PowerPoint for now.
Mm-hmm.
Alright, so there is one thing about Truffle. There is a nice little repository in GitHub where you can get a thing that's called simple language. It's on github.com graalvm simple language. You can, and there it should be really simple to test Truffle. I heard that there has some issues. So here, I just did it on my machine, clean checkout, git clone, and then you download binaries for graalvm, either Linux or Mac. And you will unpack these binaries to a certain location. And doesn't seem to hold very well.
I'm sure it works the other way out. Wire is the one, I'm sure.
Yeah, sorry, I actually got that backwards.
So you got it wrong?
I
Yeah,
did it wrong.
Alright. Like this.
Maybe you just
So
don't
now
have big
it's
enough
funny.
ears.
Cool.
Yeah, I actually think it belongs on the right, on the other side of your face. Other side of your face.
Why do I need this thing?
Just put it on the table. I'll pick up the sound.
Yeah,
I'll
sorry.
pick up the sound.
Let's see where that hits.
That's great. Are you kidding? Alright. Yeah, I downloaded this thing, I built it, and this is my directory here, which is my simple language directory. And the nice thing about this simple language checkout is that it also comes with some command lines that should easily run you some of the programs. And simple language is our example language to demonstrate Truffle features. I can show you here like example loop.sl. It looks a little bit like JavaScript, so it's just less complex. And I got here a loop that I'm testing. I got an iteration, number of iterations. I'm using the test function here, which is a loop, but the test whether r is smaller than 1 million. And what I can do is I can just hit /run, and then I say here example loop.sl. And what we're going to say is that, well, we get the number of iterations. We got the first 2 iterations, which are kind of slow because we're running an interpreter with 96 milliseconds. And then we get a line that tells us that there was a Truffle optimization done. It tells us here like the EST size, the size number of EST nodes in the method. It tells us then how much long the compilation took here, a couple of 100 milliseconds. And it tells us that the resulting code size was 409 machine instructions. And after this one gets done, like this third iteration is a little slower because we also need to compile. But afterwards, we get a huge speed up for the same program. And so this is one of these example programs here. We can look at this program here now in different ways. One thing is to look at let's just skip the middle layer and let's just go to the bottom layer. Let's just see what comes out of this optimization. And what you can do for this is you can see run_assembly. And this will run the same stuff. It's just that it will output the assembly code that was generated by Truffle when it optimized that method. And so now you can see that this thing is real, actually. And you need to know a little bit about hotspot assembly to pass this correctly, but I will explain that here in a minute. So this first headers here is just some hotspot headers that make virtual dispatches on hotspot faster. Under all normal circumstances, we would enter the program at the verified entry point. And you see here one first thing here. Anybody knows what this does? Yeah, Mario knows that, except for Mario. This looks really strange. I mean, we just entered the method, and now we are like, what?
Sorry,
And
just a quick question.
yes,
The syntax, is
the
that
syntax
load
is
or
destination, and this is its destination source.
AT&T or Intel?
Destinations.
Yeah,
Source,
it's
okay.
destination source.
Okay.
So this is
That doesn't help. We're seeing it from an opposite perspective.
So that's a load.
It's moving from
Show
the left
us
to
on
the
the
right.
screen.
sorry. Yes.
Sorry, right.
So
Is it a load
I
or a
should get
store?
it.
It is a load or a store.
This is
Yeah.
this is what we are. This is the destination of our operation,
Oh.
and this is the source of this operation. So we are loading from this address and we're storing to REX. Interestingly enough, it's. Wait a
No, I don't
minute.
think that's true. Next
Exactly,
line is subtracting from the stack pointer.
Yeah, exactly. You're right. It's actually the other way around.
This is
We're
still
storing there. We're storing that rate. Exactly. Yes. Yeah, we're storing this. So we're storing REX into this thing. So what is the value in REX at this point in the function? I mean,
It may just be storing because it doesn't know if it's used or not. So,
yeah, exactly. But why is it just storing at this address?
excuse me.
Why is it storing at this address?
Because so it can restore it after it comes back, right? After it returns whoever is using RAX and else thinks it's RAX.
Why is
No.
this?
Well, it's have its own
It's
policy
like a
dimensions.
stack limit.
Yes.
It's like a stack limit so that you don't push beyond a particular point.
Yes, correct, accurate, yes. So what we do here is this so-called stack bang. We are testing a couple of pages down the stack, so we are sure that we have enough stack left. Because in Java, if you don't have enough stack left, we shouldn't just crash, but we need to throw a stack overflow exception. And the code for throwing a stack overflow exception itself needs some stack. And therefore, yeah, you better test whether you got enough, right? So that's the stack bang. Anyway, so
And there's an unmapped page at that location, so you get a trap.
yeah, exactly. So you would get a signal. You got like usually yellow pages, red pages. Like you got these pages are protected, and you got a signal, and in the signal handler you then make sure that you will throw the exception.
So what if this move fail? Do you have like a stack overflow?
Like if this move fails, there's going to be a signal handler trap, right? And the signal handler will throw the exception. And for throwing this exception, you're not executing Java code, but you're executing native code, C++ code.
That would be
But
a
this
sig
code still needs the correct amount of stack.
file. So is this a sig file then? If
This is stack file, yes.
I'm very interested in this. The most
Right.
straightforward way of implementing this is to do a compare against, the end of stack value instead of relying on the signal handler.
Right.
How much faster does it go to use this trick?
Exactly.
You don't have an
That's what
indirection
you do in
anymore.
products, right? Find little
Exactly.
epsilons.
Exactly, not a lot. In particular on modern Intel systems, not a lot, right? The thing is just we would need an actual test and an actual conditional jump, which could take up space in the branch predictor.
And a load of the
In
limit.
particular, if the branch predictor on Intel sometimes has a coarse granularity, so if this predicted branch could basically collide with another branch that is nearby, and yeah, so there's corner cases where it can make a difference, but I wouldn't mind putting it as a comparison.
Okay.
But on the other hand, like this way you can have nicest questions to students. Yeah. Anyway, so yeah, this is source destination. Yeah, source destination because we're moving here 0 to the register, 0 to the register, and so on and so forth. But now we need to find that loop. Let me find that loop. This is usually a little awkward here, but we need to find the back jump. Well, this is the back jump because here we jump from B3EC to B to 63C0, right? Yeah. And C0 is here. So this is our innermost loop. This is the loop which corresponds to this. Let me just get. This is the loop which corresponds to this loop here, which is simple language, right? This is the loop which is this division. No, that's actually. Yeah, this one. Yeah, this is the loop here. This is the loop which just sums up I. It sums up the sum and it sums up I. Always does I plus 1 and it does the comparison against. So this is the loop. So now we look at the machine instructions that the Intel processor is going to perform for this loop. And the first instruction again looks like a little awkward. Right? It does a test of EAX and some other place. What is that about?
What does the test instruction do?
The
It's like
test
compare.
instruction is comparing this, but actually we're not using the result of the compare, we're just comparing. Just saying. So it seems
So
again
are you
we
out
have
of
to do.
Are you out of instruction space, for example?
I have instruction? No. But we are still it's still like
What
kind
does
of.
every loop need?
It needs to make sure you don't
The optimization. Why do you need a loop?
All right.
Well, and like it's like we're in a managed system, so we like let's say we don't know whether this loop will spin forever or not. We need some way to potentially stop the thread because we don't want the thread to just run forever.
You can change RBX.
Pardon?
You can just change RBX and jump up.
Yeah, but I mean, like
Right, but it needs to track back to the VM. So
yeah, it needs to track to the VM. Yeah.
And so
It's
the way
a-
you do is you have it looks like you have an interrupt by I guess whatever that memory location you make it invalid and so it'll trap.
Exactly. Yes. Yes. So it's a similar trick as with the save point, with this poll at the beginning of the method. It's just here that this is called a save point, and it's a point where I can stop the thread if I want to make a GC. Because I need to be able to make GCs quickly, in particular if I have a low latency GC, so I need to be able to stop the thread. And I would stop the thread by protecting this memory address here. And then there will be a trap, and that trap will bring me to the signal handler that will stop the thread, but later I can come back. It's not, right? So this is the so-called save point instruction at the beginning of the loop. So that's just useless type of stuff, but it doesn't actually work, right? But it's not useless in the sense that it allows us to keep the system like snappy. Because when I request a GC, when one thread requests a GC, the other thread needs to be as fast as possible at the same time.
So why test versus like a move or like just a load?
I believe test is here the smallest number of machine code instructions that you can get. And in particular test AEX because like Intel sometimes for these lower registers, REX, RPX and so on and so forth has some encoding is smaller. So the only reason here, we just want the smallest number of machine code instructions that will do this for you.
So above, why don't you use test for the Stack Overflow?
I guess you could use test. That's actually, I don't know. Yeah. A move would be here also fine, but I think it does the same thing, but because we are not interested in the result.
So I'm jumping a few steps here, but is this also how truffle assumptions are implemented?
No, but if you are going to invalidate an assumption,
Yeah.
you also need to stop the threads. Okay? So at the point in time and then the thread would be stopped here.
Right.
And then potentially from here the thread would either continue here, or if then the assumption would invalidate this piece of machine code, then you would from here jump to the interpreter. So yes, I mean the answer is kind of yes. This is how assumptions are implemented.
So one possibility is that the interrupt flag will actually be different in this case. Here, it's going to cause a read, so only things that protect read. There, you can actually only trap if you try to write something that's read only. So you'll actually cause a different interrupt flag when this happens. So you could have an interrupt handler completely change on the interrupt flag rather than on the address.
Okay.
Yes, good.
So alright, so then we got register mode, let's ignore it for a moment. So then we got here this addition of one register to another register, and after this addition we have the jump and overflow. Because in Intel every subtraction, every arithmetic instruction would set the flags, and so we can here jump and overflow to the optimization handler. And this is the sum variable, because here we have another add 1 and RCX, and this is the I variable, which always adds +1. And here we also have the jump and overflow, which is, again going to the DR10.
Well, if this is the case, why not just use the loop? If you're really concerned about code size, you should be using the loop x86 instruction. There's a loop x86 instruction that both decrements the RCX and goes to the beginning. So why aren't you using that instead if you're really concerned about code size? Yes.
Which loop instruction?
So you're having to jump back.
Yes.
And you're using RCX in order to decrement.
To increment, yes.
Or to increment.
Yes.
You can use this same mechanism using an x86 instruction.
I do not think that any of the optimizing compilers I've seen use this type of loop instruction.
I don't think so.
I thought it's slower. Like
Yeah, it may be smaller, but I think it's slower.
Is it actually slow?
So what is wrong in this code, which could be improved, which I give you, is two things. First of all, they're using here add 1 and RCX, and a little bit smaller would be inc. So we could use here an inc potential. And the other thing is that in this case, this jump and overflow is not technically necessary, because you could prove at this point that this cannot overflow because of this check. Yeah. But that's just, yeah.
Is this prologue the same for every routine? Could it be factored out?
Which prologue? There is no prologue.
Well, just this piece of code at the beginning of
At the beginning.
You mean the thing at the top
Yeah.
of the method?
the whole, this generated code, is this
So
generated code?
this is in a loop, right?
This is the
in a
loop.
Oh, this is the
Generated
loop.
code.
Yeah.
Sorry, yeah.
Yeah.
So one thing he didn't say was the overflow checks are here because in this language you have arbitrary precision arithmetic.
I
So
thought
when
we-
you do increments, if you overflow the machine size, you go into a big increment.
Yeah, you're going completely.
Otherwise, you wouldn't need the overflow check.
And then we have another jump and overflow here, and register allocator, there might be some improvement here possible, but what we do not see, because for us it looks like these moves are all useless, but because the de-optimization needs the state from the loop header, we sometimes need to keep an old value alive that is used by the destinations of these jumps. This is why this looks a little bit very awkward from a register point of view, but yeah, there could be improvements further on this loop. But this loop is already fairly tight for what they would usually produce for dynamic language type of code. And this is the comparison then against the constant, which is 10,000 or 100,000, something like that, and then we jump out of the loop. So this is just to give you a little bit of a view on this very low level. And now we'll give you a view on how we get from this high level to this low level. And we can do this by running dump. And we have a graph visualizer called ideal graph visualizer that will give us a compiler pipeline here. Oh yeah, that's that. Oh wow. funny stuff. So, all right, let's just get it a little in, and let's just remove state for now because it just makes the function a little bit smaller. All right, so what you see here first is this is all methods that you would inline through during the partial evaluation. So it's like call arguments, call proxy, execute generic, execute void, and so on and so forth. Here it's a store to a local variable going through the methods. Here it's SL less than node, and so on and so forth. But this is just the whole, like inlining through every method you would step through if you would step through this method function, right? And this is then going here. And at this point in time, you got sort of the method after inlining, which means you got a tons of so-called fixed guard nodes. So this is the compiler graph of Curl. You get tons of fixed guard nodes, which is always something like, I know this is true, and if it's false, deoptimize. Yeah, there's optimized type check, and so on and so forth. Yeah, but what then happens is that the first thing that's done here is an escape analysis. So we have one object in there, which is the frame object in truffle, right? And this object is storing the local variables. And we do not want that object to actually exist. Because if that object actually exists, then every store to a local variable becomes a store to memory. And we don't want that. And we don't have that, because in the loop, if you remember, the registers, like the local variables, were just in registers. They were never actually on an object that is allocated on the heap, right? So this is why the first thing we do here is an escape analysis that will get rid of this object and just simulate it. And just simulating the object and just knows if I'm de-optimizing here, the values for that object are in these registers or in these stack slots, right? And one interesting thing on this graph visualizer is that it allows you to give a diff. And this shows you the amount of code that is, let's just move this a little further. Yeah, this shows you the amount of code that is deleted by the escape analysis. And to give you here just a few, like, oh well, this is a little bit too small, unfortunately. Like, let's zoom a little bit out just to give you an impression of how much this is. Like every red node here on this graph is deleted by the initial escape analysis. And only the white and green nodes are the ones that survive. This is one of the reasons why, for performance reasons, we're currently considering doing the escape analysis during partial evaluation, because that might give us, for this upper part, like probably 2x speed up. But yeah, so basically we can also see this in the graph size, like after I do all the inlining, node count is 301, and afterwards the node count is 58. It's here, node count. It's 58, this is 301. Because you've just every single store and read to that frame has been virtualized and connected. So so after that, the graph already looks very sane, in the sense that, well, I mean, this is how I suppose this graph should look like. We got a loop. We got here an integer add exact with 1 coming in, which is my I plus 1. Right? I got my integer add exact with this other variable, like I, because I'm summing up I. And yeah, I got some proxy nodes here that just make sure I know which values are flowing out of the loop. This is very useful for some loop optimizations to know that, but they don't do anything. I got here the phi nodes, which just capture, like, I got a value which is flowing in from before the loop, which is 0, and I got the value which is flowing in from the loop, which comes from the backend. Yeah, and I got here the comparison. I got the loop structure, like loop begin, loop end here, and I got here a loop exit. And then I return the value, which I returned in boxed form. I boxed the integer because my return value is always boxed, right? Yeah, so this loop already looks very, very much like, you can already imagine how from this we would get then to the machine code, which you just showed, right? And if I am now a clever compiler constructor and I do a range analysis on, for example, this variable here, then I can somehow see that this if is comparing this variable against 1 million, So I will know that at this point, this variable is either 0 or it's below 1 million. And then I could, for example, swap this integer at exact with a normal integer head. And then I get a better code. That will give me like 5%. We actually have a version, like because the version which is downloadable here for Growl doesn't do that, but we have a version that does that. Yeah, this is just, and then, I mean, in this particular example, it's not very useful because most of our compiler optimizations don't do anything. But yeah, like, but in general, like these are the compiler phases that we're running through here. We do all sorts of canonicalizations, log elimination, but there's no log in that graph, right? We make the reads floating, we lower the bars, and so on and so forth. But this is a tons of optimizations that is running through this. And the final graph looks then a little bit bigger, which is here. So the loop looks now fairly similar to what we had. It's just that some of the control flow is more explicit. For example, here, this integer at exact is an actual control flow instruction where it has a true and a false branch, meaning like I was not overflowing, I was overflowing. And the other thing that's changed here, for example, is that the boxing of the integer is lowered. So the boxing of the integer, which could potentially really allocate an integer, that whole code is in that graph. And the allocation here would do prefetch allocate to make sure that we get a little bit more performance by telling the processor that this thread local buffer is important. Then we potentially write here the object headers and so on and so forth. And we got something else here, which is here a slow pass call into the VM, because allocation is even more complex, because at the beginning we need to see whether our thread local allocation is actually going to succeed, which means whether we are at the end of our thread local allocation buffer. And if you have at the end of our thread local allocation buffer, then we actually need to evacuate that thread local allocation buffer, and this is done with that for a call. But in this graph, you have now a lot more detail than in the original graph, and this is where the compiler graph gets from less detailed to more detailed, because then we can do more optimizations. And from this then the register allocator, like this is then now brought into non-SSA form, and the register allocator is run on that, and then we create the machine code.
So what you're showing us here, this is the Growl compiler, not the hotspot compiler?
This is the Growl compiler, yes.
Okay.
Hotspot has two compilers, client compiler, server compiler. This is the Growl compiler. That's the best compiler in the world.
So the Growl compiler is a completely separate compiler. It can run totally without hotspot.
It can run with Substratium, which is another project in the labs, but usually it would run on top of hotspot.
Usually it runs on top of hotspot.
Yeah.
It's written in Java.
Which parts of hotspot are you using? Just the register allocator?
No, we're not.
No. We're using like the garbage collector from hotspot, the runtime system from hotspot, and we're only replacing the compiler component.
Oh, I see.
So does Growl compiler also do like loop optimizations, like software pipelining and?
I don't know what software pipeline is. It does loop optimization, it does loop healing, it does loop inversion, but you have a check in the loop that you can get out the loop by duplicating the loop. It does moving guards out of loops. It will do some loop unrolling. It does full unrolling at the moment if a loop is only, it's a bound constant. Yeah, we do some loop optimizations. We also do vectorization. So if you get a loop that you can somehow vectorize, we recognize the vector form. Alright. Yeah, and Growl is also an open source project. It's written in Java. You can download and build it. This is the thing we just here for this simple language. We have pre-built binaries, so you don't need to also build Growl. But you could theoretically also build Growl, and then you could even do a Growl optimization for your dynamic language here, because you could plug it in. Yeah, all right. So that's for this type of stuff here. But let's go back now. This was like just showing you kind of the layers that I run after the truffle layers. And I want to show you something else now, which is I got an example program, which is example division.sl. So this example program, it's just running this here. It's similar to the previous one. You just have a parameter here which is called divide by. But yeah, we give a 1 as a parameter here. Just for the sake of it. But let's say, yeah, there's some parts of the program who give 1. I'll just give something else. And what I can do is I can then run this. Run, and then I'm saying here example underscore division. And yeah, that's just okay. That's good. We get from 99 milliseconds to about 1 millisecond here, right? And now we look at the assembly again. Okay. But now we see in this assembly somewhere, if you help me find the loop, this is the marker for the allocation code for the bar. And yeah, here's the save point pole, which is a good indicator of probably the start of the loop. And somewhere is the jump back, which is probably, is it this guy? No. This guy. Oh, maybe it is not here. No, it has to be here. This somewhere here has to be the loop. I'm jumping overflow, I'm jumping overflow, I'm jumping. Yeah, no, yeah, actually down. Yeah, same. But it goes to 880, which it means it goes to 1 above. Yeah, because we are actually interesting. Yeah, I think we're actually comparing. Yeah, we're comparing here actually the value against 1. So what would you speculate? Or maybe I did a mistake here because maybe I was not building this again. I just run this again. Yeah, exactly. Sorry, I had to rebuild. I was testing this. So all right, we got 11 milliseconds now. That was a spoiler, unfortunately. but we got 11 milliseconds now, and if we now look at the assembler, we should at some point see here an IDIF instruction. Actually, yeah. That's the one I want to see here. And so we got an IDIF instruction. Interesting enough, that IDIF instruction is actually, it's actually has all this metadata associated with it, because an IDIF instruction can of course trap, because we could have a division by 0, which will bring us to the signal handler, and which will not allow us to continue here. Right? That's why we need all of these things like oopmap and values and so on and so forth for displays, because we need everything to be able to de-optimize. Okay, but now let's do a little bit of truffle fun here. So the first thing I can do here is I will show you something that's called compiler directives. And Truffle has fun compiler directives, and the first one I want to show you is we can do like compiler directive dot or something. Let's see if this is going to give us this compiler directives. Yeah, exactly. Sorry. This is probably too small to see. Is it? Oh, is it okay? It's okay. All right. Good. So I was doing compiler directives in interpreter here. So I can in Truffle, I can check in my code whether I'm running in the Truffle interpreter or in the Truffle compile code. Okay? And so I can just say here like, all right, interpreter. All right. I can compile this. I need to build here because for some reason my Eclipse doesn't update the jar. And I can run this again. And then I will be in the interpreter. Too slow in the interpreter now. Yeah, that was my second iteration. Right. But then after I'm done with that, it seems to be my print buffer is a little bit delayed. But anyway, after I'm done with that, once I'm entering the compiled code, I'm no longer printing that. Okay? So I can distinguish code that should run on an interpreter from code that should run later. Okay? So this is this one. I can also say here like compiler directives that in compiled code, which will do the actual opposite, which is going to be
It's gonna be very slow.
alright, it's very slow. Oh yeah. Now we are like, now we enter the compile code and we have to print, right? But this is just for you to be able to distinguish stuff I only want to do at the beginning, or I only want to do in the second section. Anyway, so you already knew all this, but let's just, we have this integer left divided by right, and we want to do an optimization here. We want to speculate that we know the value of the right part, right? And the way we do this is we introduce here an integer, which is going to be add compiler. The first thing is we say here, like, this is compilation final, because I want the compiler to take the constant value of this field when it compiles. I say compilation final, I say long, and this is right value here. And what I will do is that, well, if my right equals my right value, which is like I'm actually, my speculation was okay, then I will return left divided by right value. So that's that, and otherwise I will here say, all right, I will do here compiler directive, and I will go here transfer to interpreter. So I will transfer to interpreter, and I will here assign my value to my right value profile. All right. So this would be the usual code. I have some speculation. My speculation on my profile here is the right value. And I will test whether my speculation holds. If that holds, I know that I can do left divided by right value. And if that does not hold, then I will, I will assign the new speculation. So this will be the usual code. And if we run this now on my example division file, I need to build again. Let's build that and to run the example division. Yeah, suddenly I'm a lot faster, because suddenly I can speculate that my division was 1, then the whole division falls, and in the code there's only the comparison whether my speculation failed. This is the code we saw just before. I will show it to you again. We can do run assembly, example division, and we will here somewhere have here this speculation that I'm value 1. So this speculation and this jump here to the interpreter is actually corresponding exactly to this code. I'm executing right equals 1, because 1 is our speculation. And then I'm going here transfer to interpreter. All right, what is wrong with this code?
If the right value changes too frequently, they always be jumping back.
Very good, excellent. Well, I got already a truffle thinker here. If the right value changes too frequently, we are always going to be optimized. And I want to show this by just having a little bit of a slight modification of that program, which is also here, example division polymorphic, where I'm just giving either 1, 2, 1, 2 always as the right value to that function. And if I'm now running this thing, then I will be very disappointed, because it's actually, all right, I'm running slow, then I'm optimizing, and then if I'm hitting my optimized case, I'm fast, like 1 millisecond. But if I'm not hitting the case I was optimizing for, I'm slow, I'm like 100 milliseconds. Okay. But I did here something which is, I did here transfer to interpreter, which means I'm just transferring to interpreter. I'm not actually invalidating my profile. Okay? So you would do this when you say, I assume like there should be 1 coming. If there's something else coming, it's going to be slow. But I still want to keep speculating that 1 should come here. Right? And I can quickly change that. Usually I would actually, the correct thing to do here, usually, if the code would be correct, would be to say transfer to interpreter and invalidate. So this means I'm transferring to interpreter, and I'm at the same time telling the VM this compiled code looks fishy. So it should be thrown out. What is going to happen now is that if I put this here, and I can run this. Right. So now, like, I'm hitting my optimized case maybe once here, but then I'm hitting the unoptimized case, I'm transferring to interpret invalidating, and later truffle thinks again this is hot, and I'm entering a recompile loop. Right? So this is bad. So what I want is I want to gracefully degrade to a non-optimized version if I get such changing values.
All right, I have a question. So if you bring up the code again, before you use and invalidate, right? you still have that line that says right value is equal to right. It means you're overwriting your cached value. Right? So then, for it to work properly, wouldn't you have to regenerate the code? Because it's already been inlined into the instructions.
You mean in this previous version I had only transferred to interpreter?
Yeah.
Yeah, so in this previous version I only had transferred to interpreter, which changes then the value of right value.
Yes.
But the optimized code is never actually reading right value as a field. It has already decided right value is 1.
Oh, okay.
So just because you change that value here doesn't mean this will give a different result, because at the point in time when you do your compilation final, it means that at the point of compilation you disassociate the access to that value, right? Because at this point you just say, oh, I'm not accessing the value, I think this is 1.
Okay.
And I'm just replacing it with 1. And so any further stores to that value give us, no update. Okay.
So the question is, so you didn't have this annotation compilation final,
Yes.
then, but you still had right is equal to right value. Would the generated code actually load right value from somewhere in memory and compare?
Yes. But then you wouldn't get any optimization, because then it would still just load the value.
Yeah, sure.
Because the optimization is done because crawl is able to replace the load to the right value with constant 1, and then crawl sees like, oh, I got like left divided by 1, I can optimize that. Or left divided by 8 can also be optimized because you can shift it, for example. So, but yeah, we are now at dot transfer interpreter and invalidate. Now we need to fix our code. So we need to make this slightly more complex. So what we do here is we say if right value equals 0, it means that right value was never. We say that if right equals 0, it means that right value was never. Oops. Okay. Never initialized. And so what we do here is we say if right value equals 0. So now we are in the uninitialized case, and we want to here transfer to interpreter and invalidate, because it means we were never ever executing this thing. And we are now assigning just value equals right. So that's the uninitialized case. That's good, right? So else, and now what we need actually is we need sort of a case which tells me like I'm the generic case. And I will put the generic case as just like private static final long generic equals, I don't know, I need to take some long value, which I could actually have an additional boolean here if I wanted, but just for the sake of keeping this simple, I take one long value which I say is the generic value. And so else if right value is not the generic value. Okay? So when the right value is not the generic value, then I want to profile on that right value. Then I want this type of code. I want to say if right equals right value, then I want to do my trick here, right? And else, what I want to do is I want to transfer to interpret and invalidate, but I'm not capturing now the new right value, but instead I'm now saying right value equals generic, right? And down there I will keep just in any normal case, here I will just keep here return left divided by right as my result. Right? So I mean, we can make this even clearer by saying like uninitialized equals 0, and here I say equals uninitialized, and yeah, one thing we might still have to do here, which is here we have this one corner case, which is like if right equals uninitialized, then like right value should be actually. I mean that doesn't really matter because that's division by 0, so it's anyways corner case. But what I could still do here is like if right equals uninitialized, because I don't want to keep it being in the uninitialized state, right? So I could say here like right value equals also generic. So in these cases I all go to the generic cases. Yeah. Should be compiled, yeah. So yeah, so this is just one small thing still. But here I'm right value equals uninitialized. I can do that here. When I'm in the uninitialized case, I transfer to interpret and invalidate. I was never executing this one. I will capture the value from the first execution, and then if I'm then in the not generic case, I will try to keep speculating. But when my speculation fails, I will go to generic. But you can imagine you could do now certain tricks here to say like, well, I'm just actually this is something I never tried. But what we could do is like I will do here something like I will get the milliseconds where this corner case last occurred, and if the milliseconds between now and then is small enough, I will go to generic case. But if it's too large, then I will try to keep speculating. So you could do a lot of, because here you get a choice, either go back to the generic or don't. Right? So this is still your choice, and you could still do here transfer to interpreter and not invalidate, and only invalidate when you are sure you won't invalidate. Yes?
So once you've validated it once, it'll never
Yeah,
become
in this
optimal
case it will never, yes.
So if you have a really long streak, and then you break that streak and you start another really long streak, it's slow forever.
Yes, of course. Yeah, you could still, I mean, what you could do is, that's not a question. I mean, in this case, you could still do some sampling or something, or try like after some time think like, well, maybe I try again, right? But this is still a general problem, of course, that we are degenerating here. It's a one-way street.
Is there like a library for writing these finite state machines to make it
Yes.
easier to be correct?
Yes, absolutely. Actually, that's something I can show next. But let's just see whether I did here correct and run here the polymorphic example. Oh, well, I need to it. Sorry, yes. I don't know. I have to run the polymorphic example. Right, polymorphic example is slower, but it's still not, out of bounds. And I can run the monomorphic example, which just gives you the best performance, right? So this is what we want to have. There is a library for this. Yes, let's just throw out all of the code. Let's see if I can get that one branch profile.
It's kind of surprising that a divide is 12 times slower than not dividing at all.
Yeah, I mean the divide is a very big chunk of that loop. The other stuff is very the other stuff is very like here we can create a branch profile, but I don't want the branch profile. I want the value profile. Yeah, we can create a value profile. I want here a primitive value profile. Assign this to a new local variable. Actually, I want the file assigned to a field. So I will assign this to a new local variable here, which will be final. I have a profile now. I can delete all of that stuff. And here I can say something like long r equals profile of the right value. And here I just divide by r. Alright. Let's see if that works. That's what I should build. I will later show you the code of this guy, just that you know the implementation. You can run the example division, it's fast. You can run the example division polymorphic. It's a little slower, but it still works. So this is doing exactly that one. If you go into value profile.profile, this is oh, we don't have the source code here. Is that? Oh yeah, we only have primitive value profile. Primitive value profile, the Java. Alright. I think I missed some version of this thing. It's a recent one. Yeah, this is approximately implementing the same thing. It's just more generic because it's actually working for all of the primitive values here. But it has this generic case. Yeah, it has these individual cases, and yeah, it has these different profile versions with cache misses and so on and so forth. And the cache miss goes into the initialized state, and yeah. So this is just a more complex version of this. You can find the latest version of this also as part of the Profit source code, which is part of the Graal OpenJDK repository. but it's just using the same primitives. I just wanted to give you a feeling for the underlying primitives that this other more fancy stuff like caches and so on are built on, because you can build other things with this, which would be actually more exciting. Like one of the things you can, I mean, just like these things, like let's say I actually would like to see something which is just measuring the time between the current exceptional case and the last exceptional case, and only de-optimize when this time is big, for example. Right? So there's a couple of things which could be interesting to, instead of this current very primitive form of like uninitialized state or optimized state, generic state. This is the most simple thing here.
If division is like 12 times slower, do you ever not want to do this optimization? I've never seen this optimization before.
Wow, I mean, in Java we can't do that optimization because it doesn't tell me so much. I mean, it's always good if you have the constant of a division available. Yeah. But if you don't have the divisor,
Division by 1 probably is a common occurrence.
yeah, division by 1 is the other thing, yeah. but actually, even if it's division by 2 or division by
Any power of 2.
8,
Right.
right?
Any power of 2.
Yeah, or even like sometimes, I mean, compilers do even optimizations like it's division by 10 and you kind of have just some shifts and a plus. I mean, division is an expensive operation on it.
Right.
But yeah, I think there's other things that need to be considered. I mean, this is a typed loop, and Intel's performance on typed loops is sometimes very unpredictable. Like the loop gets a little bit larger without actual so much additional work, and suddenly it breaks down. I think what actually happens is that Intel has some units to optimize loops, and probably the compiler, when it sees a division in the loop, bails out or something. So what we're seeing sometimes with loops in Intel is very non-predictable because they are running their own compiler on top of it. So we are like, I did a lot of work at some point to try to get one more register move out of a typed loop and give me like 0%. But on the other hand, there could be another loop where one register move is suddenly giving you 20% because you're falling below some threshold or some. Also, like the thresholds are based on the complexity of the loop in terms of control structure, so that can also influence it. But yeah, and I mean on standard hotspot we cannot do such optimization so much because it's harder to adhere to the interpreters some additional profiling. Whereas here it's like super easy. Yeah, and this just shows one of these powers of profile. Yeah, I'll get one more small stuff if you still have time.
Sure.
Yeah.
Do you want to take a break and then do it
Uh,
after the break?
Take
Yeah,
a break.
let's take a break. 2 minutes, 10-minute break.
I would just 5 more minutes
Oh.
and then a break. I will then, because it will not take long. I just want to show you why our simple language is better than Java. And so,
I was going to say better than Feeney, which would possibly be true.
I'll get to that.
I just get here. Then-
I should put up the generic slide that says, the opinions expressed herein are not official. Oracle Corporation.
Exactly. So I spent the time writing the Java program which would do the semantic equivalent of our simple language program, which is it will try to have big integer operations because this is the semantics of our language. But at the same time, it will try to speculate on the value fitting into a long. Okay. So that is and so this is then. I mean, first of all, it's very awkward to write in Java. It's very awkward to write in a statically typed language. It's code, because but still, it's kind of doing the thing, right? And I got this Java thing here compiled, and I run this with one of the latest versions here, which is GTK8. And I'm running this, and this is my iteration times, which is when I'm in the speculation zone here, I'm getting fairly okay numbers with maybe 9 milliseconds, 22 milliseconds, something like that. And then I'm running into the zone where I'm overrunning to big integer, and then I'm in this 40 milliseconds range here. And I can compare this now with what I got for our a simple language, which is now, I'm now comparing this against the example loop, which is the exact same code in simple, this one here. And I'm running this here. And yeah, this is actually the case where I'm not overflowing to integer, I believe. Yeah, exactly. This is the case where I'm not overflowing to integer. So if I'm hitting the case where I'm not overflowing to integer, I get down to 0 milliseconds here. Whereas Java, even for the cases where it's not overflowing yet, but it's not yet overflowing to integer, I'm in the 3 millisecond range. But then, if I am now running the overflow version, I'm still getting into the same range as Java here if I'm overflowing. So yeah, actually a little bit below, but the numbers are fairly up and down because the big integer is a lot of allocations, so it's like GC time. But yeah, I'm here like in the same range as Java here if I do then kind of degrade. And that's in general what's the result of this code and what the result should be of this code. It's like if my speculation works, I can get sometimes even tremendous speedups of 10x or more. But if the optimization doesn't work, I'm at least not slow. All right, with that, we're making a break, and thanks for your attention.
It works a bunch of things and then like that's
Oh,
what
really?
it's
Yeah,
all.
checking the code out.
Hey, look at the topic. We were just talking about that.
So I'm going to talk a little bit about concurrency, because most of what we've covered so far is language implementations that are single-threaded techniques, single-threaded VMs, single-threaded languages. Concurrency is a big field, and this is an introductory course, so there's no way I can be exhaustive in the time that we've got. But I wanted to give you some sense of some of the work that's been done, and maybe some of the opportunities that are available if you're looking for a research topic. Oops, too fast. It kind of seems inevitable, given especially if you're in the hardware world, that you have to go down the concurrent path. But it is worth pointing out that a lot of projects have survived just fine doing single-threaded stuff, right? Because you can do federation if you don't have to do a lot of communication between the different threads. If you don't have like a big common shared memory pool, and they're all fairly evenly balanced, running a bunch of VMs in parallel on a node works just fine, right? And a lot of implementations have gone that way. So you don't have to go down the route of building a concurrent system.
Sorry, I'm not familiar with the word federated.
You run independent VMs to solve your bigger problem. So you're running, say, a web service, right? And do you want one honking great big VM that serves all the incoming requests, or do you want a whole bunch of different ones running in parallel, as independent processes, maybe on independent machines, to service the requests that are coming in? So it's kind of, you federate all of these VMs to give you a big system. So there are a number of reasons why you might want to do that anyway. Hardware is really big these days. I don't know of any VM that really scales to a maximum node, that can do efficient low pause GC on, terabytes of memory and hundreds of cores. That's sort of still in the realm of research to do that well. And they certainly don't scale across nodes, so if you've got a cluster, you're not going to run one VM anyway, you've got to run one per node. No one solved that problem. So you need replication anyway to deal with faults, because if your VM crashes and you're only running one, not going to be a very good service. But on the other hand, if you really want efficiency and you need fast communication, then multi-threading on a common shared pool of memory, there's kind of nothing that can beat that. So that said, it's a big field and you have a lot of choices, and you have to look at the semantics of the language you're trying to implement as well as the semantics of the underlying hardware, and try and find a match for the kind of the cross products of all that you've got. You've got atomicity requirements from the language, atomicity guarantees from the hardware, locking memory model. Does your language have explicit concurrency in it? Are you implementing some model that you've already been given, like actors or monitors? Or are you trying to introduce concurrency? Or are you trying to do both? Implement an explicit thing and introduce concurrency? all of these things are complicated, you know, and there's many ways of introducing the concurrency and exploiting it as well. So there's a lot of choices here, which is why it's a big field, and a lot of these things, a lot of these combinations are still not well explored. Worth saying a little bit about scheduling. It's very easy to supply, relatively easy to supply a concurrent model for programming, because there are programming approaches that are easier to solve for solving certain problems, where you write stuff that looks concurrent, but it's not necessarily running in parallel. And that was the way, for example, the self VM provides that, and the Smalltalk VMs provided that, because back then everything was a uniprocessor. There were no multiprocessors. So you wanted a concurrent abstraction, but you didn't have parallel hardware. And so in those systems, what you route was a single-threaded VM that multiplexed the single thread resource across the multiple user-level threads. And that's actually fairly straightforward. It's not a big change to a VM to support that. All the Smalltalk ones did it, and all the self ones did it. And it's just not, you know, the fact that there's only one real actual thread running at any one moment makes things much simpler. But of course, when you get into real parallel hardware, then you have to deal with a real scheduling issue. And this approach of cooperative scheduling, kind of, you know, the experience is that you can't really use that. There have been a number of attempts where people have tried to build cooperatively scheduled systems on top of parallel hardware. But the problem is the underlying hardware and the OS tends to be designed around preemption and not cooperation. And so there's always some mismatch and stuff fails. It would be really nice if someone's doing hardware research or low-level system research to support some mechanisms for cooperative scheduling in the hardware and or OS. For example, years ago I proposed a mechanism for very lightweight save points, where you could basically set a bit in a register that said, okay, trap at the next save point, and every backward branch would look at the bit. Right? So it's very cheap to do that in hardware. It's even patented. The patent, it's so old the patent's going to expire soon. That's how long ago that was done. So if if any of you guys are working like on RISC-V architecture, you want to support high-performance VMs, there's a whole bunch of things that have been tried in this field. Some of them actually implemented. That technique was actually implemented by Azul, so it does work. What about concurrency and interpretation? Well, interpreters are slow, so it's not really, you're not trying to parallelize the interpreter to make it fast. The idea is that, you know, you're spending your time in the compile code and not in the interpreted code. So it's not really a goal to try and make the interpreter go faster through the use of concurrent hardware. However, what you don't want is for it to go a lot slower. And there are a number of techniques which we've already done and used, which you can't really use in a concurrent environment efficiently because they have safety problems. So bytecode rewriting, right? You don't want to lock around every bytecode you execute to check whether it's the bytecode that was there before. All of these things that involve rewriting the instruction stream at the bytecode level are problematic because the rewrites are not typically atomic. You know, multi-byte instructions span weird boundaries. There's no atomicity guarantees usually from the hardware at that level. So all this stuff where you take a bytecode sequence and you look at it and put a new one in, unless it's a 1-byte write, you can't really do that in a concurrent environment. Even the truffle stuff, right? The ASTs are per thread because we're doing node rewrites, and those things are not thread safe. So we run in the systems in the lab where we have parallelism. We run separate copies of the ASTs per thread. An area for research here is how there's not a heck of a lot known about how threads interact with profile feedback. So you've got two threads running stuff. Each of them is generating its own profile. How do you combine those profiles to generate code? Or should you not combine them? Should you just generate independent code for the independent threads? Because they might be doing different things and you might want different optimization decisions. I can't think of a single paper that's explored that issue. Yet it seems like an important issue to me. Completely open field in that What has been explored, and hence I can provide lots of slides on, is object synchronization, particularly the monitor form. Monitors have been around since the 70s, and they hit the big time with Java, which put them in as the synchronization technique associated with objects. And then suddenly, there was big money in making them go fast. So you need to, if you're implementing monitors or a monitor-like system, you need to deal with object locks and fast locking. So in Java, if a thread owns the lock on an object, it can call any other synchronized method, and that happens a lot. And the lock's released when the last such method is executed. So first guy in owns the object, can do what he likes, and when you exit, you release it, and the next guy can come in. So you have to count how many nested monitor enters you've got and match up with the monitor exits. And I mentioned in the early section on Java bytecodes that because those are implemented via separate bytecodes, they can be unpaired in the bytecode stream. There's no way you can generate unpaired monitor enters and exits from Java code, but of course if you get bytecode that's generated some other way, they can be unpaired, and the implementation has to detect that and throw an error if it gets an exit without a matching enter. So the simple way to implement this, and how it was done in the very first Java VM, is to just have a separate lock table, which is, you typically hash into this lock table using the object ID. Inside there's an OS level mutex, and that all works, but it's really slow because the hashing has to be done every time you do a monitor enter. The OS level mutexes, are not so fast either. And then you've got the recursive things. You've got to deal with the fact that you tick the lock multiple times and you release it multiple times, which the OS stuff usually doesn't account for. So that's easy, but it's slow. So you want a fast technique, and there's been a lot of work on this over the years. The papers kind of peter out about the late 2000s, but there were a whole bunch of papers from the late 90s through the early 2000s. It seems like we've kind of settled on a solution now, which is what I'll describe. There are a few variants, and if you look through the literature, you'll see little tweaks here and there, but this is the overall solution. Now, the best kind of locking, of course, is no locking, which is the benefit of doing escape analysis, where you inline a bunch of synchronized methods, and when you came in, you grabbed the lock. So if you couldn't inline a synchronized method, well, you already know you hold the lock, so you don't have to do anything. You can just elide the monitor enter, monitor exits when you do that, and that's a big advantage of escape analysis in Java. But if you need to lock, most techniques rely on observed properties of existing programs. So in most programs, most locks are uncontended. They're acquired only by one thread and released by one thread. Once a thread has acquired a lock, it frequently reacquires it by calling a nested synchronized method on it. So you have to deal with, you want to make uncontended locking fast, and you want to deal with the case where you reacquire the lock with nested monitor enters and monitor exits. That has to be fast. The contended case is not so common. Of course, once you've made all this fast, then the contended case becomes important, and you have to deal with that, but there's less in the way of literature around that. So how's it done in Hotspot? I'm going to base on this paper from 2006. There are probably a few tweaks since then. I haven't had time to go look in the sources to see whether there's much more, but this should give you the basic idea. So the tag bits in an object's header word encode its lock state. There are a couple of bits in the header word that are used for various purposes, GC purposes and other things. So one of these combinations is reserved for GC. But the other three represent an unlocked object, a thing called a lightweight lock, and then the heavyweight lock is the thing that uses mutexes and condition variables and all of that stuff, and has the slow path for contended locks. So what you want to do is go from unlocked to lightweight and make the lightweight locks optimize the uncontended acquisition and the nested acquisitions really quickly. And there was a pretty clever scheme devised by Lars for the very first hotspot, which is that when you execute the first monitor enter on an unlocked object, you copy the header word into a reserved slot in your stack frame. So because you know you're in a synchronized method, you can reserve a slot, copy the header word into that slot, and you cas a pointer to that header word into the existing header word. And that has the low order bit set to indicate there's a lightweight lock taken. So if you do that cas and it's successful, that means you've acquired a lock and the original header word now is in your stack frame. If you do subsequent monitor enters by the same thread, you compare to see whether that pointer points into your current stack, because you know where your stack begins and ends. If it points into like your stack, it means you own it. And in that case, you don't have to do anything with the lock record, but you do have to do the comparison. And then if you want to know the number of lock records on the stack, well, that's the number that indicates the locking depth, and you could release them accordingly as you return from the frames. And there's routine stuff in the exception handling code that does that looks at the stack frame, knows whether you're in a synchronized method, and does the appropriate thing, knows when it's going to drop to 0, checks the lock record. Sorry, it doesn't know, it has to check, and then copies the frame, the header word back in. And if someone needs the header word, they can follow the pointer to find it. So you check the tag bits. If it's locked, then the header word is at the target, and anyone can do that because it's just in memory. So a further improvement that came along was to use bias locking. And the idea of a biased lock is that the lock's kind of biased towards a single thread. That thread has a cheaper sequence for locking it and relocking it than other threads. And so there's an extra bit added, the biasable bit, which is down in the low order words. And up in these other bits, when it's biasable, there's a thread ID stored in there, which indicates which thread it's biased towards. So in a biased implementation, if the cas was successful, you try casing in the biased version, and then if it was successful, your thread ID is there and it's biased towards you. And if it's been biased, then you don't have to do anything about the lock and unlock operations that are nested. You just ignore that. But if you tried locking it in a biased form and you failed, that means somebody else tried locking it in a biased form and succeeded, and that's bad because you don't want to bias a contended lock. So what it does in that case is it uses the save point mechanism to bring everybody to a stop. The other guy has gone off running with an owned lock but biased, and you want to undo that. So you bring that guy to a, well, you have to bring everyone to a stop because you don't know who it was. Although I guess you could use the thread ID. I don't know why it does that. Okay, but anyway, the implementation brings threads to a stop and uses the compiler-generated debugging information to walk up the stack and sort of fill in the lock records as if it were lightweight locks, and sets the state to be a lightweight lock. So that sort of turns off the biasing in the case that it was used incorrectly. And that process is, of course, expensive. So if that happens a lot, then bulk rebiasing is done, which is all the biasable instances of a certain type are reset. Because what they found in the paper was empirically, certain types have the biasing works great, and for other types the biasing doesn't work really well, and so they turn it off selectively by type. This is Java object type. If it still is you're getting these bias revocations for a particular type, then it does a bulk revocation. It sort of stops everything, scans through the heap, fixes all the header words of all the biasable instances, and then says, okay, no more biasing for that type. We turn that off. We'll just go back to the old locking, the slower sequence. And this technique, yeah.
Why would you do this rather than say transactional memory?
Because transactional memory didn't exist at the time, or do you mean software transactional memory?
No, hardware transactional.
No. This was 2006. Okay. There was no transactional memory. There have been a bunch of studies using transactional memory for Java locking.
I imagine it works really well.
And
you get rid of this bias now.
Yeah, I think the results were all very positive. I don't know whether they've actually put it into Hotspot for the hardware platforms that support it, but If they haven't, I'm sure it's high up on the list.
Right.
I'd have to go look at the sources to see whether there's any.
I think that the bias blocking, as it is right now, I don't think that even hardware transactional memory will be the same performance.
Really?
At the moment, it's really
Well, transactional memory operates based on the fact that you're probably the one that's usually using it, right?
Yeah, it's the
And
same
so
speculation
it's
in
the same,
effect.
It's the same assumption, so it should work really well, but the transactional memory is lower.
What's the memory state like on the Intel I haven't looked at the Intel implementation to see
I
what
don't
you
know
what
how
you
Intel
need to
does
keep, because this is just a few bits, and it might be hard to compete on the memory demands.
Right, but then the cost of you don't have to do this. The
Yeah.
reunification is you don't have a
Yeah, right.
reunification problem.
Right. So they go into a lot of effort to avoid the case where revocations start happening a lot.
Right, you can avoid all that
And-
overhead.
and you can avoid that.
Yeah, I agree.
But whether the fast path
the
is fast.
path, I mean,
fast
you
enough.
cannot get the fast path of bias blocking faster.
Yeah.
No, it's probably about the same then.
Yeah, that's the same.
Yeah, it's the same, but
Right.
failure mode is much easier.
Okay.
Yeah.
Okay. There were a bunch of studies done at CERN when there was a transactional memory implementation that was going into an earlier Spark processor. But that got cancelled, so I wasn't very helpful in terms of.
RISC-V has had plans to put it in.
Right, okay. This would be a good study to sort of look at this again and have a simulation in both directions and see which one's good. But it certainly would simplify things, for sure. A couple of other noteworthy tricks. So as I mentioned, the monitor enters and monitor exits might not be paired. And rather than trying to detect that in compiled code, the approach taken in Hotspot is it attempts to prove that they are paired. If it successfully proves they are paired, then it generates compiled code. But if it can't prove they're paired, it says, this is going to be interpreted. So anyone who writes funky monitor enter, monitor exit stuff, where the compiler can't do the analysis and figure out the pairing, it's going to run slowly anyway, because it's just going to be interpreted. Okay, last couple of things. So code management and patching in a concurrent environment is sort of notoriously tricky. And this is mainly because we do it a lot in VMs, and hardware designers and OS designers never assumed anyone would do this a lot. And so the mechanisms are not very well tuned. In VM you need it in all sorts of places, in like caches, and if you're resolving classes and patching code, or you're linking to new code, or you're flushing old code, all of that involves code modifications. Even on a uniprocessor, you have to be careful, because on a uniprocessor, unless you go back and read a really old uniprocessor, there's a pipeline, and the pipeline behind you can have stuff that's already been fetched from the locations you're modifying. So you still need a pipeline flush after you've done a code modification before you try executing stuff behind you. And that's a horrible subtle bug which I've seen before. When you're on a multiprocessor, you also have to flush invalid code out of the iCaches. And it's easy enough to flush your own iCache, but what about flushing somebody else's iCache? If it's coherent and you don't have to do that, that's great, but mechanisms for doing this on most architectures that don't have coherent iCaches are really painful. And you might also get the memory model doing weird reorderings on your writes to code, so you have to have a code patching sequence which is safe no matter what reorderings that happen. So, my recollection is in the Spark manual, you have to do this weird patch where you write the instructions backwards in such a way that there's always some kind of a valid sequence with a skip at the front or something. It's really contorted. And in general, this is really tricky. You have to spend a lot of time reading and understanding the processor manual for exactly what's legal. Most ISAs, as I said, assume this is rare, and they don't make any guarantees about timeliness. So if I patch stuff here, the visibility of the patch on some other core, it's like, well, eventually, is what most architectures will say. Yes?
Is it not used like a mechanism where they just map a new executable page when they patch?
Well, so what you do is, No, I don't think so. I don't think I've seen that. Yeah, usually what you do is you compile and generate code in some area of, new area, and then you have to patch in branches to that from various places. So like, if you have a new method and you have inline caches that were pointing to the old method, the inline cache has to be invalidated and the branch that's the inline cache has to be patched. So, I guess you could write the whole new code and switch it in, but that's pretty heavyweight. It's a pretty heavyweight kind of operation. Usually you just do the writes and you try and put the barriers in to make sure the writes propagate in the correct manner. The other potential benefit in a concurrent environment is if you've got abundant threads, you can do compiles in parallel. So most high-performance VMs now maintain a queue for compilation, and the mutator threads are running through, tripping counters and invalidating inline caches and stuff, and that generates requests to the compiling. They get put in a queue in a separate thread, or maybe several threads, drain the queue, run the compiler, generate the code, and then, atomically install the code into the code cache and the lookup system. So the trick there is making sure that the atomic patching is done right, but you have to do that anyway for other mechanisms, and you also want to make sure that the compiler, which is now running potentially somewhat delayed from when it was invoked, the world hasn't changed so much between when you put the thing in the queue and when the compiler actually runs that it gets confused. So it has to check its assumptions when it runs.
Mario, are you aware of anyone who does iterative compilation, where you run low optimization, medium optimization, high optimization this way?
In a queue, usually the lowest optimization stuff is done immediately. The tier 1, tier 0, as it's sometimes called, is usually literally just in time or just too late.
Do they start?
Those are queued. Yeah, hotspot is a compilation queue.
Okay, and it does it increasingly levels of optimization.
It has several levels. Okay, you're going to probably have some foreign code you need to deal with, precompiled libraries, either stuff that you've got elsewhere or stuff that's linked into the VM that's not written in the application language, and that might not have save points, use its own calling convention if it's foreign code, etc. If you're calling into that stuff from a concurrent VM, because it doesn't have save points and you can't do anything really other than suspend and resume it, then what you typically do is you have a barrier that you cross as you exit the VM into the foreign code, and a barrier when it comes back in. And if you need to suspend it for some purpose, you suspend it when it hits the barrier. Otherwise, there's kind of no point in suspending it. Usually when it's in native code, just let it do what it was going to do. It's presumably manipulating its own memory, etc. You might have a similar barrier if it tries to invoke operations that mutate objects in the heap. So for example, if you're running a GC, you'll close the barrier. Everything that's running foreign will carry on doing its own thing, but if it tries touching the heap, then it will be suspended until the GC completes. And so you need this locking system on the barrier to make sure you either stay in or you stay out, but you don't cross when you're not supposed to. That's all I have for this week. Next week, I'll look at memory management in a concurrent environment, including a little bit on concurrent GC. We're going to have Michael van der Vatte come in to talk about tooling and VMs, and we'll do the competition stuff as well. For the remaining half hour, we can look at code. We've got more slides from Thomas. If anyone has questions about the truffle exercise or doing more truffle stuff, or if you're planning to win the competition with your truffle submission and you need hints, we can help you with that too.
I'll release people submitted benchmarks by tonight, so you guys don't get blindsided by.
Is there a homework for next week?
No, isn't there?
This is it.
Congratulations.
There may be one more reading thing which I haven't decided on yet, but that will be all.
Can we send benchmarks tonight? We did miss
You're sending it tonight.
Yeah.
Set a time.
Because I'm gonna try and get to everyone by tonight.
All right. Yeah.
Let's say, like, 7 at the latest.
Sure.
Yeah.
You wanna go for your remaining slides?
Benchmark versus lines of code.
You wanted to do something where lines of code versus performance.
Oh, yeah.
Yeah, so you don't really have time to do that in this mini week. But what I think I'm going to do is gather all your implementations of all your exercises, and if I can do this without massive amounts of human intervention, I'll run each one, count the lines of code, can measure the performance, and report back with a graph of how things varied with each exercise. But that will be later, after I've recovered, and after I've gathered everything from Patrick. So I'll post the results, on Piazza. I assume the Piazza website for the course will exist more than.
Oh, it exists for many years.
Yeah. So I'll post stuff back there, and let you know what I find. And if I find something really interesting, we'll write an educational paper with everyone's name on it.
What do you?
I've always wanted to do the CERN, 500 author paper. That probably just works if you leave it there.
Right, yeah. I have some more high-level slides about the Graal and Truffle projects that I'd like to quickly show you. This is just an overview of the type of stack we're covering with Graal and Truffle research at Oracle Labs. And this includes here some high-level language runtime type of research that we're doing with R, Ruby, JavaScript implementation, some graph analytics. Then you can go to lower-level runtime type of work, which includes partial evaluation stuff, dynamic object model research we did, that also Mario presented some of it today. And then we have some high-level compiler construction things. These are now going into the Graal layer, but higher level. This includes escape analysis, locking elimination, SSA form, doing some vectorization, getting these de-optimization checks optimized, sort of on this level. And then we also have some really lower level compiler construction type of work where it's about getting the regis allocator better. We're currently trying to do a better trace allocator, for example, for Graal, and trying to use the Spark hardware as good as possible. But the nice thing about a research lab like Oracle Lab here is that we have experts for this whole stack, and we have a project that are spanning this whole stack with 30, 40 people on it. Regarding Graal and Truffle, these are the main parts that we are developing at Oracle Labs here, and these are the main languages we are developing. There's a JavaScript engine, there's a Ruby engine, an R engine, and we are also doing C. So we are also interpreting C on top of the Truffle system and then dynamically compiling C. This allows us to have a safe C, for example, with bounce checks, and this allows us in general to combine C programs with the rest. Because we found out that C itself is not enough, we also want C++, Fortran, Rust, whatever, we decided to do a LLVM bitcode frontend, and this is what is currently being worked on with students in Linz and Manchester. And this will allow us to run all of LLVM languages on top of Graal as well, in addition to the dynamic languages. Then you can integrate those two. All right, so that's just a high-level picture. I was talking a little bit about the Java compiler. Graal is a Java compiler. This is the URL for OpenJDK, for the OpenJDK project. You can download, build Graal there, run it, import it into Eclipse. And yeah, it's open source on the GPL v2 license. And the main goals for Graal, the main theme of Graal is first, it has aggressive optimizations as a first-class concept. So it's really designed for graphs that have a lot of de-optimizations in them. And some of our dynamic languages, including JavaScript, we have more guards than actual operations. And this is why it's very important to have the guards optimized. Another focus of Growl is it has like the best escape analysis that's available right now. There's some partial escape analysis that allows you to push the object allocation as far out into uncommon paths as possible. There's a thesis from Lucas Stadler on that available as well. And finally, Growl itself is very modular. It's a modular Java application where there's 50 different modules, and you can very easily hook in your own optimization phase, if you like, into Growl. Well, the truffle framework, this one is available on GitHub, and this is the URL to this simple language on GitHub, which I was demonstrating today. It includes also all the scripts that I was running today. And you can, for the ideal graph visualizer, you will need to check out of Growl. Like you get Growl, the ideal graph visualizer, and you can run simple language scripts. And also for your own truffle language, it's maybe not bad to start to download this thing and just swap out the language implementation, because you can reuse the scripts which have the commands in them to print the assembly, the commands to print to the ideal graph visualizer, and so on and so forth. Yeah. For truffle, the main idea behind it is it's a single definition of language semantics in an interpreter. So if you look at Google V8, if you look at SpiderMonkey, they all have multiple layers of JIT compilers, and it's very hard to innovate in these languages. And this is also why, at the current point in time, we are the most complete JavaScript engine that supports most of the ECMAScript 2015 tests. Yes.
So is that graphic on the right accurate? Do you do all that truffle?
It's accurate. You can do all that in truffle. We have a brain fuck implementation. Yes, I got it on my laptop. I can show you it runs really fast. Yeah, we're not yet doing Haskell, but Haskell would actually be interesting. We have a closure prototype, but it's not public yet.
You also have like some very unusual languages in there, like ACTA.
Yeah, I have to admit this is more marketing type of.
I see.
Because
it would be, I find it unusual if you get any real performance gains on those particular languages.
I agree.
Because there's very little dynamics in it.
Yeah, I agree. I mean, you can get performance gains on C, C++, for example, because even in C programs, more complex C programs, we use function pointers. And when you have function pointers, you can have inline caches.
Right.
Or this division by a constant, for example, is also something you could profile in C. Right? So even if the language itself is a static language, you would think you can get performance gains. Also with C, like the inlining is not designed to be in any way related to the hot parts of the program. So you can gain there.
Right.
But there's some languages out there which are so weird that it seems at the moment hard to see how we could optimize them.
You would have to change the garbage collector for some of these languages because they rely on the fact that they're single write once, so you can just get rid of it immediately.
Yeah, I agree. And I take this as a good feedback. I will modify that cloud to only the languages that Truffle supports on it, because by now we have enough languages on Truffle that it will make a nice cloud. And this is from the early slides that we didn't have yet, so we were just putting out something.
So I understand that the LLVM bitcode implementation is still something that's being developed, but what opportunities for optimization do you see there? Because you're down at that level. I don't know if you have access.
Yeah, so this is still developed, but we will push this open source under the name Sulong in a couple of weeks actually on GitHub. So you will see the LLVM implementation or the starts of it. Let's say for LLVM we don't have so much interest of speeding up the actual LLVM program. There is two main interests. One is we want to be able to execute these LLVM programs in a sandbox without performance loss. And there is speed up opportunities. Because the C compiler, if you would put all the bounce checks in, doesn't do a very good job in optimizing them, but our compiler can do that. So we'll be able to execute the LLVM in a sandbox. So no buffer overflow problems and so on and so forth. And this can be very interesting because, like, for example, the heartbeat bug or something like that, that's actually one of our milestones. We want to be able to run the code that was causing the heartbeat bug in Truffle LLVM and show that this bug would not have been possible. Because we think we can execute this with a very minor overhead, maybe 10% something in this range, because you need some more checks, but you can do a lot of optimizations to move the checks out of loops to get them out of the way. So this is the first interest we have in this. The second interest in this is we want this LLVM-based approach to help us integrate LLVM-based languages and truffle languages. So here it's about, I want to be able to call from Ruby to a Ruby C extension method without having a call boundary. And in particular also the other way around. We have some really nice speedups for Ruby there because, right, it's one thing to rewrite all of your inner loops to C, but then these inner loops sometimes need to access Ruby data structures because they are accessing Ruby array, they're accessing Ruby object. And then this access back from C to Ruby is not optimal. It's not the best way to access it because the runtime system is really able to generate better ways to access it. So here it's more about speeding up the integration between those two. There are some opportunities where you might be able to outperform a C static hash of time compiler because of the dynamic, like better inlining of the hot parts, getting function pointer crossings. For example, in GNI is an interface between the JVM and native code, but it's always function pointers. It's always a call boundary. When I'm getting a method ID for a method with GNI, I'm always crossing a function boundary. It's always an indirect call. But these are function pointer calls that can be, with inline caches, can actually be combined. So I believe there's not zero opportunity there, but realistically speaking, I don't expect anything. I expect that we'll be able to run this in a safe mode, if necessary, and we also expect this to bring us these languages together. We have with Truffle, we have also this nice thing of language interoperability, where I can have one language pass the data structure to another language. And there, we also want to have C and C++ participate. So like a JavaScript object, I pass it to C, and the C code will then access it. And all of these tricks are only possible if we also bring the C code via LLVM into our compiler infrastructure. Yeah. All right. Yeah, we have a JavaScript engine. This one is at the moment not open source, but we are working on that. Yeah, but it's actually one of the most, it is the most ECMAScript 6 compliant engine right now, because for us it's just so much easier to add in these features because it's just an interpreter. It's a lot easier, less manpower intensive to add this than, I think, yeah, the most crazy thing out there is like the engine that's in Safari, which is 4 tiers. So it's 4 different compilers, like one interpreter, 3 compilers. And of course, if you want now to change the semantics of your language, there's 4 places to look. So, of course, like if you have enough manpower and money, like Apple, there's ways to overcome that problem, but in general, it's still.
You're from Oracle and you're complaining about Apple?
Well, there aren't many bigger entities we complain about. So.
Yeah, exactly.
We take our opportunities where we can.
Exactly. It's a general theme, right?
And they have conservative garbage collections.
We're just a small, we're just a small company. We're only 30 billion.
Yeah,
exactly.
We're a startup.
Yeah, compared to Apple, we are a startup. So, yeah. Right, yeah, we got Ruby runtime. Ruby is on GitHub and open source as well. So they are very active there. It's one of, there we are using actually parts of Rubinius, which is another Ruby open source project, to rewrite parts of the standard library in Ruby. Because one issue we're having with Ruby and R all the time is like compatibility problems with the libraries. You can get to a completeness with the language, but you also need the libraries to work. And that's harder. Here in Ruby, we decided to rewrite as much as possible of the core library in Ruby. Yeah, that's the Ruby runtime. We got an R runtime. R is a statistical language for vectorization. It's our most challenging language that we're implementing. So it's really stressing the limits of the system in terms of what it can do, but looks very good right now.
Can you describe why it's so hard?
Yeah, absolutely. So, like the way I see it, like it has like the only data structure it knows is vectors. That's the first thing. So there is not the concept of a single value. Every value is a vector. Every operation is a vector operation, at least conceptually. Then it has things like every assignment to a local variable of these vectors, which are arrays, is a copy, logical. And then it has things like every argument is a promise. So it's not actually evaluated at the time when it is given as an argument to the function, but at the time when the function first accesses this parameter.
So it's lazy,
Lazy, yes.
Not properly.
not properly.
Yeah.
Sort of
It's
lazy.
not a problem. I mean, like the additional thing is like that the interpreter has sometimes some weirdness that we need to be bug compatible with. But in general, this in and itself is a problem. It's lazy evaluation of arguments. Then it is you can overwrite any operator, including the parenthesis operator.
Left parenthesis is a function.
Then what else?
About design language, how?
Yeah, it's like there's a lot more such things. So, but it's like crazy.
But basically, if you
There is
look at a
something
piece of
worse.
source, unless you assume nothing in the language semantics has been modified by the surrounding code, then you understand what it is. But until you've looked at everything else and eliminated all the possible redefinitions,
Yeah, and like every
you really don't know what it does.
yeah, and every this operator can be redefined in any of your outer environments, and the outer environments are very complex.
Right.
And like basically just like if you one more thing,
I
which
assume
is
it's a common case of programmers are not doing this because it increases the complexity for them too.
The really weird stuff, yeah, you don't see. But of course, you have to deal with it. If you
Right,
have
I
a
mean,
complex
that can be
implementation.
incredibly slow if you
And
want.
there are certain weird things which you just wouldn't want to deal with, like you can revert an expression back to its source, modify it, and reevaluate it.
yeah, there's one more thing, which is that
Oh.
every value is immutable. So if you're assigning actually to a single array element, like if I'm assigning to a single array element, then logically the whole array is copied.
Right.
But actually you don't even know that because this the assignment operator is an operator that calls a function, right? Which is there's
Okay.
In short, you have to inline incredibly deep before you find out what's actually going on.
I see.
and you need a lot of assumptions about your surroundings before you can say, yes, this is an array access here and I don't need to copy the array.
Right.
But the good news is like there's speedups possible a factor 100 and more if you do it properly.
Does R do any of those optimizations, or does it just do super naive?
It's a bytecode
No, it just do
interpreter.
none of this.
But I mean, it's doing all the copies also.
It
has
has the same.
It has a 1-bit reference count.
Yeah.
If it's only referred to from one place, it doesn't copy.
Yeah, there's a reference counter, but it's in general interpreter, which is very slow for scalar values. But if you have very large vectors, the interpreter overhead is amortized, but it's not completely amortized. So even if you have very large vector operations, because we can fuse loops with crawl and the whole stack, we are able to get like speedups of 2x, 3x or more.
With the vector stuff, all the intermediate vectors are materialized.
Yeah.
That's the big problem. So if you look at some R programs that manipulate, only say 100 megabytes of data, some of them run out of memory in a 4 gigabyte heap because they're generating so many intermediate copies of the
Yeah, I mean the whole language has dynamic typing, and that's the other thing. And then the array access operator is kind of Turing complete in the sense that you can use almost any value as a potential index into an array, including a Boolean vector, including an integer vector. This integer vector can have positive values to select elements. It can have 0 values to select nothing. It can have NA, not available, to select not available. It can have minus values to select everything except for these columns.
I get the idea. I want the high level stuff, not all
Just say. You can look at the piece of code, which is the R interpreter here.
Oh, and the other thing is there's no language definition. It's just an implementation.
And it has a native interface which is not documented. And anyway, it's our problem, right? It's our problem. This is the native front end. I was already talking about that. But now we've already started with that, and we'll go public with that soon. which is element bitcode interpreter to draw in LLVM-based languages. Yeah, that is part of the team. I'm now doing kind of the advertisement pitch. This is some acknowledgements of some guys working on this. There's a lot of people in Oracle Labs that worked on this project. We have a lot of interns. This is definitely an incomplete list, but I just can't fit more on the slide. And yeah, we got a couple of collaborations right now, which is probably also an incomplete list. But yeah, you shouldn't. This is a big project. There's a lot of people involved. And yeah, this is our working environment. Come to us as an intern. Yeah, we are looking for interns, both in America but also in Zurich. This is in Zurich, where we have an operation in Europe. And yeah, we're looking for interns who are interested in anything in the stack from upper level to the lower levels. I showed you these 4 levels. We usually would select one of them for an internship. And yeah, I think we have a very great team. And if you're interested, please shoot me an email. We definitely want to further increase the investment in that thing because it looks very promising right now. And yeah, we hope that this will empower a large stack of compiler technology in the future. All right.
Okay. And if you have projects you want to pursue, if you're interested in using any of our stuff, then we'd like to hear from you too. We have plenty of project ideas.
All right.
Okay, so we got 15 minutes before the survey guys come in. Stick around for that. Say nice things.
All right. So we got more time. That's good.
Rare. I can't remember last time we did something that even before the time runs out.
I don't know why they scheduled it for this week or not next week. Well,
No, undergrad classes ended this week.
Oh, okay.
Yeah.
All right. I don't know this process at all. So. I was just told to leave 15 minutes at the end.
Yeah, I can try one more demo if you like.
I have a question.
Yes?
Would you ever use like x86 assembly and try and inline that directly rather than like trying to interpret C or like parse LLVM bytecode? Because you already have the assembly.
Like, I think it would be possible, but it would be more complex than the LLVM bytecode.
One of the things I worked on before all of this stuff was a binary translation system that used the hotspot approach to do binary translation. And we built a prototype, actually using the hotspot server compiler as its translator with the jar front end locked off, that would ingest x86 code and emit machine code, so basically simplified RISC code, so Spark without the register windows and the delay branches. So very vanilla RISC code. And we got very good translation results from that. So I don't see any reason why, without some effort, and I'd be unwilling to put a quantity on the effort, that we couldn't do the same thing using this. I mean, I'm sure it wouldn't be just, write some truffle notes and some special and suddenly you have a wonderful binary translator, but the general approach has been proven to work.
Yeah, I think it will be more complex, but I think it could be working. We are starting with element bitcode. Maybe we have to go to binaries as well, because at the moment we assume that you have the source code available of the thing we are including.
You'd lose a lot of information that you'd want for optimizations, right?
You lose a certain amount. The hardest part is reconstructing the understanding of what the memory structures mean. So you can't do much with that, but you still can reconstruct a lot about the control and data flow between registers, condition variables, functions. One of the nice things is that function calls. It's just another control flow. So you could inline. We were inlining our compilation unit size for the stuff we were doing was on the order of 100,000 instructions. So it's a pretty big compilation region, and we were taking big chunks like the entire path of the inner loop of a TPCH query out of the database, and using that as a translation unit, generating machine code for that, and eliminating all the weird side branches that never happen and all that stuff. All these techniques work quite well.
There's a question on the left.
Yeah, so LLVM actually IR has inline assembly. So how, do you just not handle that, or
At the moment, we're not handling that, but we want to handle that.
Because GCC, playing with 04 will generate inline assembly on regular C++ code. So
I think we can handle inline assembly. I think it should be possible at least a certain amount. But yeah, at the moment we're not handling it.
I was also interested in the hard bleed analysis they hope you do. How is it that you plan on doing that? So it's not a use after free bug. It's not a traditional use after free bug.
It's a bug that there is a memory access into a
Yes.
region that's not allowed. So we
But
would
it's allowed statically from C code, but they use the internal allocators. They allocate a big page, and they use the internal free. The internal free doesn't actually free anything, and then they did use that for free quotes. So it wasn't the libc free.
yeah, but at the point when you free it, you mark the memory as like you're never allowed to access it anymore.
Yeah, but
So anybody who would try to access the memory that's free is going to.
yeah, but it's not libc's free. It's their internal mycool free function.
Right.
So you have to modify the original program too.
Yeah.
So that was
Yeah,
the.
yeah.
It wasn't completely
Absolutely.
automatic.
No, I mean, and I just read out there is something.
Well,
it
open-
didn't.
OpenBSD has that protection. When you free something, it's segmentation fault to use it afterwards. But that doesn't catch hard free because it wasn't truly free.
Okay.
You know, but maybe they can do this use of the free detection in particular. Because we have the garbage collector available, we can determine whether something is really free. Because there's a lot of work on safe C with fat pointers or something, but use of the free is still a very big problem for them because if you use a fat pointer, like a pointer that points into a table, you still want at some point to deallocate that table or that slot in the table.
That's when you use garbage collector type shrink.
Yeah, exactly. Yeah, for this you need a garbage collector type analysis. And,
It seems like a lot of the heartache in implementing some of these languages are things that just kind of seem way too dynamic philosophically. And do you think that there's like a good feedback loop with the reference implementations that we should maybe hold off on some things because
Yeah, don't do dumb stuff in your language design. is a you know, if more language designers understood the consequences of the designs, life would be a lot better in terms of making those things run quickly. But because we've had more or less 20 years of scripting languages evolving to become very widespread that are all built on interpreters. In the interpreter, it didn't cost anything to do some of these things, but it's very hard to generate code for some of them. And so it would behoove language designers to understand more about what's hard to do and what's easy to do. And that's why, the stuff Lars was doing with Dart, right, that was all driven by an implementation team who knew how painful some things were and they tried to avoid those things. But it'd be good if there was more of that going on generally.
Yeah, and I mean, there's a feedback. We try to install the feedback loop a little bit. For R, for example, we try to add some flags where certain weird features should rather throw errors than being actually supported. But yeah, I mean, it's very hard to get language implementers who have their interpreter to adopt this because they are to a certain extent a competition. And the more weird the language is, the harder it is for the competitive implementation, which uses a compiler.
You guys may not be the right people to ask, but even so, is Oracle doing, so you have various JITs and Graal and these other things. Has anyone ever thought to actually port to actually do Graal hardware that will speed up languages instead, rather than doing it in software?
In general, I can talk to you a lot about that. In general, there's not a heck of a lot in ISA design that we
Not necessarily ISA design, say FPGAs, for example.
Compiling to FPGAs? No, not really.
No, not really.
Not really. Not really. I'm very skeptical actually about that as an approach.
Yeah, I mean, there could be approaches that help us with some of the code. Like, for example, I mean, Intel itself, for example, with this jump and overflow and things like that is already very much.
But Intel also just bought Altera, so there may be value in this.
When it's partly chicken and egg in that until there are widespread available FPGAs and common platforms, there sort of isn't much commercial interest in going down the path of using an FPGA.
You're a research lab, so you're supposed to be looking ahead.
We'll look at it a few years.
It's like-
Yeah, I'm just
Like a 10-year
skeptical that
horizon.
an FPGA is a good substrate for general purpose computing.
Intel is starting to put FPGAs into some of their chips for
Yeah.
Microsoft.
I think there might be some very limited
Yeah.
uses where it benefits, but
Microsoft
for
is putting them
general,
in there now, and their servers are all FPGAs in them.
But with it,
So, I mean,
I'm still skeptical.
Yeah, I mean,
The difficulty with FPGAs is kind of, you have a substrate in which you've already sort of discarded a factor of 10 in, area and performance and power. And so you immediately have the barrier of climbing
Sure,
and
but
getting
people
all of
target
that back
GPUs.
again before you've
these
even got
FPGAs
parity.
are also pretty small.
but
Yeah.
people still target GPUs, for example, so
Well,
they also give it
I'm just as skeptical about GPUs, to be honest. GPUs, are designed for one characteristic, which is graphics. And they don't have to be good for anything else. So I think we have to leave.
Yeah.
thanks Thomas again.
Okay. Yeah.
So go ahead. So I have to get out of the room too, right?